So let's start chapter 7. So remember before I give you a heads up that chapter 6 in particular, the last two parts of chapter 6, which were the central limit theorem and the normal approximation to the binomial probability distribution, those last two concepts were actually the most, objectively, the most confusing and difficult of the entire semester. But once we overcame those, chapter 7, you'll see, will be much more simple relatively. So chapter 7 is going to be on confidence intervals. Intervals, not intervals. So remember on the very first day of the semester, we talked about the motivation for the class and the purpose of the class. And we used a motivating example of, let's say on your next job, you're tasked with the assignment of finding what percentage of all Americans approves the president. And then we said that we couldn't get data about the entire population of interest. We couldn't get data for every single data point in the country. So we had to resort to a much smaller subset in the form of a poll or a sample. And then from the poll or the sample, we asked, how do we make a correct conclusion about the entire population from just that smaller number? And from that first day of class, we kind of took a detour and probably what felt like mucking around in the woods, in the weeds for a while. And it turns out that now, finally, we're done doing all that and we're ready to address the motivating question, finally. And we're ready to go back full circle. And so, especially nowadays, elections are coming up in full swing. And so this issue of polling, you're going to see new polls, multiple polls every day, day in, day out for the next few months. So let's revisit this issue. So let's say that you have some population of interest, like the country. And we gather some much smaller sample. So let's say, for example, our sample has a size of 100. And let's say that from that sample of 100 people, you ask every single one of the 100 people, do you approve of the president? And let's say that 43 say they approve of the president. So we're going to call that X. X is the number of people who say they approve, the number of successes. So let's say X is 43. But that's just the raw number of successes. What would the proportion of success be? So the proportion of success is the number of successes divided by the number of the sample. So because the number of the sample is conveniently 100, it'll just be 43 divided by 100, which is 0.43, or 43%. And the variable that we use to notate that is going to be this symbol here. This will be lowercase p with a pointy symbol over it, and it looks like it's wearing a hat. So the technical term for this is p hat. So p hat is the proportion of success in the sample. It's going to be 0.43 or 43%. So that's just for the sample of 100. So what we're really interested in is the true proportion or percentage of success for the entire population. So based on this one number, can you say that the proportion of success for all 300 million Americans is also 43%? Yeah, so you can't say it's exactly 43%. So what conclusion do you think you can make?
I feel like the sample size would be too small to really conclude anything, but if the sample size was bigger and you still got 43%, then you could conclude that it's around that number. for the
Okay, very good.
population.
So you can't conclude that it's gonna be exactly 43%, but what you might be able to conclude with some hand waving is that the true percentage is around 43%. So the conclusion you might make here is the true percentage that approve the president is around 43%. Of course, if you actually reported that and stated that to somebody, that the true answer is around 43%, they're gonna look at you funny and with raised brows and say, well, what do you mean by around 43%? So this ambiguity here is what statistics is trying to quantify. So we're gonna quantify what this, this hand waving, this around actually means. So nowadays, and moving forward, when you read these poll results in the news, you'll see results that look something like this. So if you look at poll results in the news nowadays, you'll see something that looks like this. So what this means is that this number is coming straight from the sample that was collected. So this means that in the sample that was collected, 43% approved of the president. But again, we're trying to extrapolate a conclusion for the entire population, not just for the observed sample. So this second number, after the plus or minus, is something that we call the margin of error. That means that the true percentage of all Americans in the country that approve of the president will now have a certain range associated with it, a certain interval of possible values. So that interval will have a lower bound and an upper bound. So what's the upper bound? Or what's the lower bound in this interval?
40%.
Yeah, 40%. And then what's the upper bound? 46%. Okay, so this is saying that the true interval in the country that approves of the president, the true percentage will be somewhere inside this interval between 40% to 46%. And then, if you look at poll results in the news, technically there's also this third number. But the third number often confuses people. So it's usually not plainly stated. It's often buried under fine print. So if you hunt for the fine print, you'll probably see this third number here. And what this third number means is that the true percentage of Americans that approves of the president will be somewhere in this interval between 40 and 46%, and that'll be true 95% of the time. The remaining 5% of the time, the true percentage might not be in this interval at all. It might be completely outside the interval. It may be lower than 40%, it might be greater than 46%. But 95% of the time, the true percentage of Americans that approves of the president for the entire country will be somewhere in this interval 95% of the time. Any questions? Okay, so basically then, any conclusion that you can make about the population just from a sample basically has to have an interval of possible values, and it has to have a confidence level associated with it. So collectively, this is called a confidence interval. So a confidence interval has an interval of possible values, and it has a confidence level associated with it. So a confidence interval consists of a confidence level as one of its components, but keep in mind that they're distinct things. So a confidence interval is different from a confidence level. So a confidence interval consists of an interval of possible values with a confidence level associated with it. Any questions? So the interval of possible values, you notice, comes from, if you look above, it comes from a sample value that you observe directly from the sample, and that's technically called a point estimate. I don't need you to memorize that, but if you see that in your book, you know what it represents. And a point estimate comes directly from the sample. So observed directly from the sample. This 3%, as an example, is margin of error. Margin of error. And this is something that is calculated. And we'll talk a little bit how to calculate that margin of error. So this is calculated. And this confidence level, in this example being 95%, that is something that is either given to you or chosen by you. So this is not calculated. This is either somebody tells you to use this number, like on a test, or your boss tells you to use this number. Or if not, if you're independently doing this, then this is a number that you choose to use. So this number is given to you or chosen by you. Okay, so of these three components, one is directly observed from the sample, so you have no control over that. The other one is either given to you or chosen by you, so we'll talk about the consequences of using different numbers here later on. But the last number, the margin of error, that's the only one that is calculated based on the other information. So we'll talk about how to calculate this margin of error now. So, if you look at this equation, it looks hideous. But after we talk about it, it won't be so bad. So, let's talk about the individual variables. So, we talked about this p hat already. What does that represent?
The proportion of success.
Proportion of success, but specifically from the sample. So, notice it's wearing a hat. So, that's going to be a sample variable. So, this is the sample proportion of success. And using the example numbers that we had talked about before, let's say that our sample has a size of 100 people, and let's say the number of successes, or the number that say they approve the president, is, let's say, 43. And so p hat, the proportion of success, would be 43 divided by 100, which is 0.43. So in this example, the sample proportion of success would be 0.43. Any questions? Okay, and so here in this formula, we have this z, and then we have this right subscript that is this entire expression, which is alpha divided by 2. So this alpha divided by 2 is one quantity, which is the right subscript of the z-score. So this whole thing is one quantity, ultimately one number. And that one quantity or number is being multiplied by the result of this entire square root. And that square root is, for this whole expression, p hat times q hat divided by n. So let's go ahead and, we'll talk about the z-score last. Let's go ahead and just fill in these other numbers first. So p hat is the same as this other p hat that we already used, which is 0.43. So q hat is what you would expect. It's the complement of p hat. So if p hat is 0.43, the complement is what's left over from 100% over 1. So it would be 0.57. So conceptually, p hat represents the proportion of success of the sample, and q hat represents the proportion of non-success in the sample. So if 43% of the sample approves of the president, that means that 57% of the population, or of the sample, does not approve of the president. Okay, and then divided by n, which is the sample size. In our example, it's going to be 100. So the only thing that's left is this quantity, the z alpha over 2. So let's talk about what that means. So first of all, the confidence level is given to you, or chosen by you. And so let's say that the confidence level were 95%. So the confidence level, I'll abbreviate it as CL, equals 95%, or 0.95. So alpha is this defined as the complement of the confidence level. So alpha is 1 minus the confidence level. So in this example, what would alpha be? You got 5% or 0.05. So that's alpha. So in this formula, you see that there's an alpha over 2 here, divided by 2. So what would alpha divided by 2 in this example be?
0.025.
Yeah, it would be half of 5%, which is 2.5%, which is 0.025. And so that's what the alpha divided by 2 here is. And then finally, if you put it all together for this example, we're looking at z with the right subscript of alpha over 2, which in this example would be z with the right subscript of 0.025. And so if you converted this to a picture, what we're really trying to find is if we have a bell curve, we're trying to find the z-score whose right area is this much. So the right area of the z-score we're trying to find is 0.025. So how do you think we can find that? So we're trying to find this z-score, this boundary, whose right area is 0.025 under the bell curve.
Central limit?
Well, not quite. Central limit theorem has to do with the distribution of sample means. Right now we're not dealing with sample means, we're dealing with a distribution of individual values. So this is just, if we have a bell curve and, yeah.
Would you subtract that, or subtract that number and then see where it is on the, like, z-score, area?
Yeah, very good. So basically, we have this bell curve. We know that there's a table that gives us a relationship between the z-score and the area to the left of that z-score under the bell curve. We have a relationship, the table gives us a relationship between z-score and left area. So if we knew the left area, we could use the table to find the z-score. Right now, we know the right area. So we just convert this right area to a left area. So what would the left area be?
0.975.
Yeah, very good. So the total area under the bell curve adds up to 1. So this left area would be 1 minus the right area. So that would be 0.975. So now we just use the z-score chart to find the z-score that has a left area of 0.975.
How do you know that 0.025 is the right area?
So this is just notation, and that notation just has this definition of this z-score with this right subscript means find the z-score that has this right area.
Oh, okay.
So this right subscript here, the meaning of that is a right area. So we're trying to find the z-score with that much right area under the bell curve. So that much right area is the same as a left area of 1 minus that right area, or in this case 0.975. So we're going to use the z-score chart to look up a left area of 0.975 and see what the corresponding z-score is. So go ahead and so just flip to the second page. And the way this table is laid out is negative z-scores and positive z-scores. But ours is going to be a positive z-score because the data point is to the right of the mean.
Right.
So it's going to be on the other side. And so the first column is z-scores, and all these middle numbers are left areas. So if you know one, you can find the other. In our case, we want to start with a left area of 0.975. We're going to start in the middle and look for the closest one to 0.975. And we'll find the corresponding z-score for the first column.
Got it.
Okay, what are you guys getting for the z-score? 1.96, very good. Yeah, so first of all, this is negative z-scores. You know that this is going to be positive. What? So positive means, so in the table, you know the table divides into negative z-scores and positive z-scores. And we said that a data point has a negative z-score if it's less than the mean, and it'll have a positive z-score if it's greater than the mean. So because you know that this left area is greater than 50%, you know that it has to be on the right side of the mean, so it has to have a positive z-score. But if you didn't realize that, the point is that if you try to search for a left area of 0.975, you won't find that number on the negative z-score side of the chart. Exactly, so we want to look for a 0.975. And then you want to find the closest left area to 0.975. And because this is searched for so often, this table will actually have a star normally around where it's found, but then if you follow the star, there's going to be an arrow that leads you to the exact answer. So at 0.975, if you follow the star in the table, it'll show you that the exact z-score is 1.96. Anybody have any questions? Yeah, so look for, 0.975, and that would normally occur. Let's see. So, yeah, I was thinking of these two, but it turns out that 975 occurs, directly in the table.
Okay,
If it didn't occur exactly in the table, then it would be between these two values where the star is, and then you could follow the star to get the exact answer.
okay.
Yeah, but in this case, it shows up. Exactly.
Would be 1.96.
Yeah, it would be 1.96. So this z-score ends up being 1.96. So this is the same z-score that you would use in the formula. So. So now you have all the pieces of your formula here, and now you can easily use this to calculate P, and you notice this P does not have a hat on it. So this P is the proportion of success in the population, which is what you're trying to find, and it equals this interval of possible values. So let's go ahead and calculate this right quantity. But let's calculate the thing after the plus or minus first. So what did we call this quantity after the plus or minus in our confidence interval?
Margin of error?
Yeah, so the quantity after the plus or minus, that's the margin of error. So let's go ahead and calculate the margin of error first. So the margin of error is just this expression after the plus or minus.
How many decimal points do you want to put?
Oh, right now it doesn't matter so much, but let's say 4.
You want the answer?
Yeah.
Alright, I got 0.0970.
Okay, so let's say 0.0970. So that's the margin of error. This is a very small decimal number. Sometimes it's easier to express small decimals as percentages. So what would this be as a percentage?
9.7.
Yeah, 9.7%. And likewise, this 0.43 as a percentage would be 43%. So this is an interval of possible values. What's the lower bound and upper bound on this interval?
$33.3.
Okay, so 33.3 is the lower bound. What's the upper bound?
52.7.
Yeah, 52.7. Okay, so after applying this formula, what this means is that this is the answer to our question, which is what percentage of all Americans actually approve the president for the whole country, not just the sample. So the answer is going to be somewhere inside this interval. It will be between 33.3% to 52.7%. And that would be true, the percentage of the time that corresponds to the confidence level. So that'll be true 95% of the time. That corresponds to this confidence level that we had used when we calculated the z-score. So again, this is true 95% of the time. So the important thing is that the true value for the whole country, the population, is somewhere inside this interval. So you don't know whether it's closer to 33.3 or you don't know whether it's closer to 52.7. You can't just assume it's smack dab in the middle. You can't assume that it's exactly the midpoint. All you know is it's somewhere inside this interval, 95% of the time. Any questions? Okay, so this is with the sample that we have here, with a sample size of 100, and this observed proportion of success. So what would happen if you reported this conclusion, that this represents the true proportion of all Americans that approve the president? What do you think the reaction would be?
Everyone would say it's BS,
Yeah,
cause
what's
it's
that?
too wide of a margin.
Yeah, very good. So this interval, the gap of this interval is so wide that you don't know what the true answer actually is. You don't know whether it's closer to 33.3 or closer to 52. And it makes a difference whether it's closer to 52 or closer to 33. So people would not be satisfied with this conclusion because the width of this interval is so large. And the width of this interval is so large because if you look at the previous step of how this interval was generated, it's coming from this number from the sample plus the 9.7% minus the 0.97%, and that contributes to the total width of the interval. So the width of the interval is so wide because this margin of error is so large. So how do you think we can cut down the margin of error?
You could increase the confidence level.
Okay, so that's one way, but we'll talk about fudging with that confidence level later. What else could you do? Yeah.
You can increase the sample size.
Okay. Okay, very good. So you can increase the sample size. So imagine if somebody else was trying to answer the same question of what percentage of all Americans approves the president, and they had a sample size of 1,000. And the number of people in that sample that approve the president, let's say, is 371. What would p hat, or the proportion of success, be in that sample?
0.37.
0.37, which is 37.1%. But these are for the respective samples. What we're interested in is the true proportion of success for the entire population. So do you think the true percentage of Americans that approve the president will be closer to 37.1% or closer to 43%?
37.
Yeah, it would be closer to this 37.1% because there's more data. So to reduce the error in the conclusion, we want to increase the sample size. So let's go ahead and do that. So for this case, let's go ahead and substitute in different numbers here. So which of these numbers changes when we make these new substitutions? Yeah, the n is going to change. Anything else? Yeah, the p hats are going to change because this is a different sample, and p hat is directly observed from the sample. So this will now be 0.37. 1. This is the z-score change. Yeah, the z-score is based directly on alpha, which is directly based on the confidence level. And the confidence level is still at 95%, it doesn't change.
For the z-score, once we have the alpha divided by 2, are we always going to subtract 1 from that to find the z-score?
Yeah, so alpha is always 1 minus the confidence level. So if the confidence level is 95%, alpha will always be 85%.
No, but for the actual z-score.
Yeah, and the z-score will come from that alpha that we just found. So if the confidence level doesn't change, then alpha doesn't change, and thus the z-score doesn't change. So the z-score will still be 1.96 because the confidence level of 95% didn't change. And then the p hat and q hat will respectively change. So this will be 0.371, and this will be 0.629. So let's go ahead and calculate the new margin of error here, which is this expression after the plus or minus.
be about 2.99%.
About 3, so let's say 3%. Let's say 0.03, so that we can say 3% down here. So just like we expect, the margin of error decreased a lot from what it was previously. So it went from 9.7% to now only 3% as the margin of error. So the final interval of possible values is gonna be whatever you observed in your sample, which is 0.371, plus 3% in one direction and minus 3% in another direction. So the total width is just twice of 3%, which is 6%. So now the total width is much less than what it was before. And that was from reducing the sample size, increasing the sample size, margin of error goes down. Any questions?